Hello, and welcome back to the Quiet Cosmos. Tonight, the destination sits closer than any world this channel has visited before. The sun itself, close enough to warm one side of your face on a clear afternoon, and yet leaving almost every meter of the space between here and there with no warmth of its own. That contradiction sits at the center of tonight's journey, a star fierce enough to light an entire solar system, whose outer atmosphere still runs hundreds of times hotter than the bright disk directly beneath it. A puzzle nobody has fully solved, even after a century of careful looking. Before that journey properly begins, if unhurried science like this is the kind of company you enjoy at the end of a long day, a quiet like or a subscribe helps a small channel like this one find the people who are actually searching for it. And it costs you nothing more than the time it takes to tap the screen. So tonight we move from the outside in and then back out again. Past a disk so familiar it barely gets a second look. Down through layers of fusion, pressure, and boiling gas. Out through an atmosphere that somehow runs far hotter the farther it gets from the surface. Into a wind that never stops blowing. And finally, forward across billions of years toward an ending already written into the physics of every star of this size. We begin, simply enough, with the plain view of it, low in the sky or high overhead, the one object bright enough to make every other star vanish. Look up on a clear day, and the sun outshines everything else at once. It is a small, blinding disk that appears, by a coincidence of size and distance, about half a degree wide, roughly half the width of your little finger held at arm's length. That number matters more than it first seems, because the moon happens to carry almost exactly the same angular width, despite being a completely different kind of object. A coincidence this journey will return to later, once the sun's true scale has been measured properly against it. For now, the disk overhead looks calm and steady, almost featureless to the naked eye. A single smooth circle of light, rather than the churning, layered structure that any closer instrument reveals beneath that even glow. Ancient observers across nearly every culture on Earth built calendars, temples, and entire systems of time around the slow crossing of that one bright circle, long before anyone understood what it actually was or how far away it sat. A single steady disk from a back garden, and underneath it an entire unfinished physics problem the moment anyone looks closer. That steady, white gold light overhead is, strictly speaking, closer to plain white than to yellow, and the warm tint most people associate with the sun is added later, by Earth's own atmosphere, rather than by the star itself. Sunlight arriving from space carries every visible color mixed together in roughly equal measure, which combines to the eye as plain white. Passing through kilometers of air, the shorter blue wavelengths scatter away from the direct beam far more easily than the longer red and yellow ones, leaving the light that reaches the ground very slightly shifted toward the warmer end of the spectrum, especially close to the horizon where the path through the air is longest. Photographs taken from orbit, above that scattering layer, consistently show a sun far closer to a plain, blinding white than to the golden circle painted in children's drawings. The color people picture is not a property of the star at all. It is a small trick performed by the very air standing between it and every set of eyes looking up. Size like this is hard to hold in mind, so it helps to try a direct comparison. Roughly 1,300,000 Earths could be packed inside a sphere the size of the sun, if there were any way to hollow it out and pour them in. Laid end to end, more than 100 Earths would barely span the Sun's own diameter, a single planet reduced to little more than a large freckle against that scale. And yet, for all that bulk, the Sun accounts for the overwhelming majority of everything in this solar system by mass, with every planet, moon, asteroid and comet combined amounting to only a small remainder once the star itself is set aside. Over 1 million Earths would fit inside it, and it would still be carrying almost all the weight in this solar system on its own. Despite that staggering size, the Sun's average density turns out to be surprisingly modest, only a little greater than plain water, and far below the density of any rocky planet nearby. That single detail hints at something important about what the Sun is actually made from. Almost entirely hydrogen, the lightest element there is, with a smaller portion of helium mixed through it, and only a faint trace of anything heavier scattered here and there. Near the center, crushed by the weight of every layer pressing down from above, that same light material becomes many times denser than lead or gold, despite never stopping being gas in the technical sense used by physicists. Near the visible edge, by contrast, the material thins towards something closer to the air several dozen kilometers above sea level on Earth, barely substantial enough to call a surface at all. The Sun is, in a very real sense, both far lighter and far denser than instinct suggests, depending entirely on how deep into it the question is being asked. This channel has described many rocky worlds already. The Sun, unlike any of them, has no solid ground anywhere inside it, at any depth, under any amount of pressure. There is no coastline where gas meets rock, no floor for anything to settle onto, only a continuous run of hydrogen and helium that changes state gradually as pressure and temperature climb, from a thin outer haze down to something so tightly packed near the center that ordinary chemistry stops applying to it entirely. Physicists studying the Sun's interior describe it in layers all the same: a core, a middle zone, and an outer zone of boiling gas. But those layers are defined by behavior rather than by any hard boundary a falling object could feel or measure directly. Tonight's route works down through those same layers, and then back out again. From the searing core, where the Sun's light is actually made, to an atmosphere so thin and so strangely hot that it barely resembles the calm disk seen from any back garden on Earth. At the very center of the Sun sits its core, a region only a small fraction of the star's overall width, and yet responsible for essentially every bit of light and warmth this entire solar system depends on. Temperatures there climb to roughly 15 million degrees, a number so far beyond ordinary experience that comparisons stop being very useful, and pressures build to hundreds of billions of times what Earth's own atmosphere exerts at sea level. Under those conditions, matter no longer behaves the way it does anywhere on a rocky planet. Atoms stripped almost entirely of their electrons, moving as a churning mixture of bare nuclei and loose charged particles that physicists call a plasma. It is this crushing combination of heat and weight, built up from the sheer mass of every layer pressing down from above, that makes the core the only place inside the entire Sun where nuclear fusion can actually proceed. Every photon of daylight, every calendar built around the seasons, and every living thing counting on that daylight ultimately traces back to conditions found only within this one small, furiously compressed region at the center. Fusion inside that core proceeds mainly through what physicists call the proton-proton chain, a sequence of collisions in which hydrogen nuclei are forced together with enough force to fuse into helium, despite their shared positive charge normally pushing them apart. Left alone at ordinary temperatures, two protons would simply repel one another and drift apart. But under the core's extraordinary pressure and heat, collisions happen often enough and hard enough that a small fraction manage to fuse regardless, releasing energy in the process. Several intermediate steps carry the reaction forward, protons combining first into a heavier form of hydrogen, then further collisions building that up step by step into a stable nucleus of helium, with a burst of light and other particles released along the way at each stage. Each individual fusion event releases only a tiny amount of energy, but multiplied across the staggering number of reactions happening every second inside that small central region, the total output is enough to light and warm an entire system of planets stretched across billions of kilometers. A chain of small collisions, repeated on an almost unimaginable scale, is the quiet engine behind every sunrise this planet has ever seen. The overall result of that chain is a slow but relentless conversion of mass directly into energy, following the same relationship Einstein famously described linking the two. Every second, the Sun converts roughly 4 million tons of its own material into pure energy, a figure vast enough to sound alarming until it is set against the star's total mass, which is large enough to absorb losses of that size for billions of years without any meaningful change to its overall bulk. None of that converted mass disappears in any mysterious sense. It is simply transformed, following the same physical bookkeeping that governs every reaction anywhere in the universe. Matter and energy remaining two versions of the same underlying quantity. Even across the Sun's entire lifetime so far, the total material lost this way amounts to only a very small fraction of its overall mass, an accounting detail easy to misjudge without seeing the numbers laid out directly against one another. A star can spend 4 million tons of itself every single second, and, on the scale that matters to it, barely notice the expense at all. It would be easy to assume that fusion is happening everywhere throughout the Sun's enormous volume, but only a comparatively small central region, deep inside the core, ever reaches the combination of temperature and pressure required for hydrogen nuclei to fuse at any meaningful rate. Move outward from the very center, and conditions ease quickly enough that the reaction essentially stops, leaving the overwhelming majority of the Sun's hydrogen sitting completely unfused, layer after layer of ordinary, unreacted fuel wrapped around that one small active region, like insulation around a furnace. This detail matters for understanding how long a star like this one can keep shining, because the true fuel supply is not the Sun's entire bulk, but only the portion that ever becomes hot and dense enough to actually react. Estimating how long that supply might last, and how it slowly changes the core's composition over enormous stretches of time, is one of the central problems solved by the models astronomers use to describe a star's whole life story, a subject this journey will return to much later tonight. What keeps that furiously hot core from either collapsing further under its own weight or blowing itself apart is a very simple balance that physicists call hydrostatic equilibrium. gravity pulling every layer of the sun inward, while pressure generated deep inside pushes outward with almost exactly equal force. Should fusion in the core happen to speed up even slightly, the extra heat generated raises the pressure pushing outward, causing the core to expand a little, cool a little, and slow the reaction back down again almost immediately. Should fusion instead slow down, gravity gains the upper hand for a moment, compressing the core further, raising its temperature, and speeding fusion back up until balance is restored once more. This built-in feedback is part of why the sun burns so steadily, rather than flaring wildly or fading unpredictably from one day to the next. A self-correcting furnace, held in check by nothing more elaborate than its own weight pressing against its own heat. Every quiet, unremarkable sunrise depends on that same balance holding steady, moment after moment, for longer than almost anything else this channel has ever described. Pressure at the very center of the sun climbs to something like 250 billion times the pressure of Earth's own atmosphere at sea level. A number too large for most everyday comparisons to hold on to with any real meaning. What keeps that crushed material counted as gas is not how tightly it is packed, but how its particles behave. Atoms there have been stripped of their electrons entirely, leaving bare nuclei and loose charges free to slide past one another the way a gas requires, never locking into the fixed pattern that defines a solid. Physicists call this state plasma, a distinct fourth state of matter that can be squeezed far beyond ordinary gas densities and still keep flowing rather than freezing into place. Move outward from that crushed center, and the pressure eases by a similarly enormous factor, layer after layer, until it settles into something closer to ordinary air pressure near the visible edge, many hundreds of thousands of kilometers further out. Nothing about the ingredients changes across that whole span, only the weight of everything piled on top of them. Two very different kinds of particle are produced together in every one of those fusion reactions deep in the core, and they behave in almost opposite ways once released. Photons of light and tiny, nearly massless particles called neutrinos. Neutrinos interact so weakly with ordinary matter that the overwhelming majority pass straight through the entire sun as though it were barely there at all, escaping into space within seconds of being produced, carrying a small but genuine record of what is happening deep in the core, out into the wider universe almost instantly. Photons face a completely different fate. Produced in that same crushed, crowded core, each one is almost immediately absorbed by a nearby particle and re-emitted in a new, effectively random direction, a process repeated over and over across a journey so tangled that escaping the sun entirely takes far longer than anything measured in seconds. That difference, one particle slipping straight through and the other trapped in an extraordinarily slow crawl, sets up the very next stage of this journey outward from the core. Leaving the core behind, a photon of light enters what is known as the radiative zone, a vast shell of extremely dense material through which energy moves outward almost entirely through repeated absorption and re-emission, not through any bulk movement of gas. Each individual step in that process covers only a tiny distance before the photon is absorbed again and sent off in another, essentially random direction. A pattern physicists sometimes describe as a random walk, progress measured not in a straight line, but in a slow, wandering stagger. Because of how thoroughly random that stagger is, the net outward distance actually covered after each step is tiny, compared with the total distance traveled, zigzagging back and forth, sideways, and occasionally even inward again, before finally drifting a little further out than before. Estimates of how long this stage alone takes vary depending on the exact model used, ranging from tens of thousands of years on the low end to figures closer to a few 100,000 years on the high end. An extraordinary span for a single burst of light to spend simply working its way outward through one star. Whatever the precise figure, the light warming a face on a clear afternoon began its own private journey inside that core, an almost unimaginable stretch of time before it ever slipped free of the radiative zone at all. A thin layer lies near the outer edge of the radiative zone. Astronomers call it the tachocline, a narrow region where the sun's rotation changes character rather sharply from one side of it to the other. Deeper inside, in the radiative zone itself, the entire body of gas rotates almost as a single solid unit, every layer keeping roughly the same pace as its neighbors. Just beyond the tachocline, in the boiling zone still to come, different latitudes and different depths begin rotating at noticeably different speeds instead, sliding past one another rather than moving together. That narrow band of shear, where two very different styles of rotation grind quietly against one another, is widely suspected by researchers to play a central role in generating the sun's magnetic field, though the exact mechanism remains an active subject of study, not a settled conclusion. A thin seam, only a few percent of the sun's own radius thick, sitting quietly between two very differently behaved layers, may be doing far more to shape the whole star's magnetism than its modest size would ever suggest. Cross that seam, and the character of the sun changes completely. From the slow, orderly crawl of light through the radiative zone to the churning, restless motion of the convective zone lying just above it. Here, energy no longer creeps outward step by step through countless tiny absorptions. It is carried the remaining distance to the surface by bulk movement of the gas itself. Hot material rising from below, while cooler material sinks to take its place, in a pattern closely related to the way water heats and circulates in a pot left on a flame. This layer makes up roughly the outer third of the sun by radius, a churning shell wrapped around the calmer zones beneath it, constantly rearranging itself as fresh, hot material pushes upward and older, cooled material folds back down to be reheated once again. Compared with the extraordinarily slow crawl of light through the radiative zone below, this final stretch to the surface takes a comparatively short time, days to weeks rather than tens of thousands of years. A sudden acceleration after such an extraordinarily patient beginning. The last leg of the journey outward is, by a wide margin, the fastest part of the entire trip. Photograph the visible surface of the sun in enough detail, and that boiling convective motion becomes plainly visible as a fine, constantly shifting pattern astronomers call granulation, a texture resembling grains of rice scattered edge to edge across the entire disk. Each individual granule marks the top of a single rising column of hot gas, spreading outward as it reaches the surface, cooling slightly, and then sinking back down again around the bright center, all within a lifespan of only 10 or 20 minutes before that particular cell breaks apart and a new one takes its place nearby. At any given moment, several million of these granules cover the visible surface simultaneously, each one typically about the size of a moderate country on Earth. An entire planet's worth of hot, rising gas fitting comfortably within a single one of these short-lived shapes. High-resolution images taken by modern solar telescopes show this pattern constantly reshuffling itself, cells appearing, brightening, darkening at their edges, and vanishing within minutes, a restless texture completely invisible to the naked eye from the ground. What looks from Earth like a single smooth, calm disk is, up close, an entire surface never once sitting still for more than a quarter of an hour at a time. Beyond the smaller, quickly changing pattern of granulation, a much larger and slower structure called supergranulation covers the same surface at a different scale entirely. Cells tens of thousands of kilometers across, rather than the far smaller granules nested within them. Where individual granules last only minutes, a single supergranule can persist for the better part of a day. A slow, wide cell of rising and sinking gas, with countless smaller granules bubbling away across its surface the whole time, like a wide, gentle current carrying a great many smaller ripples along with it. Astronomers first identified this larger pattern not by looking directly at brightness, which barely changes across it, but by tracking tiny shifts in the motion of gas across the surface, material flowing outward from the center of each cell toward its edges before sinking down again at the boundary. Magnetic material tends to gather preferentially along those boundaries, concentrated by the outward flow within each cell, creating a faint network pattern that traces the edges of a structure otherwise almost invisible to ordinary observation. Two different scales of the same restless motion, one nested inside the other, both moving the same underlying heat, the remaining distance toward the visible surface above them. Watch the sun's surface carefully over several weeks, and a further pattern emerges. Different parts of it are not turning at the same speed at all. Material near the equator completes a full rotation in roughly 25 days, while material closer to the poles takes something closer to 35 days to come back around to the same position, a spread physicists call differential rotation. A rocky planet like Earth cannot behave this way, since every part of a solid body is locked to every other part and must turn together. But a ball of gas has no such obligation, and each latitude on the Sun is free to slip past its neighbors at its own pace. Astronomers track this uneven spin by watching how sunspots and other surface features drift across the disk over successive days, timing exactly how quickly features at different latitudes complete their own private circuit. A star large enough to hold an entire family of planets in its grip still cannot manage to keep its own surface turning together as one single piece. Most people picture the Sun's surface as one simple layer. More precisely, it is a thin layer called the photosphere, only a few hundred kilometers thick, set against a star more than 1,000,000 kilometers across, a shell thinner in proportion than the skin on an apple. Below the photosphere, the gas is dense enough to be almost entirely opaque, blocking light from escaping directly, while above it, the material thins out quickly enough that light finally slips free and travels onward without being absorbed again nearby. That transition is what actually defines the visible edge of the Sun, not any change from gas to something more solid, but simply the depth at which photons stop being trapped and are finally free to leave. Astronomers sometimes describe this boundary as the layer where the Sun becomes transparent to its own light, a definition built entirely around visibility rather than around any physical flaw waiting underneath it. Every sunbeam anyone has ever felt on your skin began its final, unobstructed dash to Earth from this one thin, unremarkable shell. Temperatures at the photosphere average around 5,500 degrees, a figure that sounds immense against anything on Earth, yet counts within the Sun's own structure as one of the coolest layers found anywhere in the star. That single number is often treated as the sun's defining temperature, quoted in textbooks and used to classify the star among others of similar type, even though it describes only this one thin outer shell rather than anything closer to the center. Calling it a surface at all is, strictly speaking, a convenience rather than a precise physical description, since there is no boundary here that a falling object could ever strike or settle against in any solid sense. It marks instead the exact depth at which the sun stops being able to hide its own light. The last layer, dense enough to keep photons captive before an almost empty run-out into open space begins. A number borrowed to describe an entire star belongs, more honestly, to only its thinnest and most transparent skin. Scattered unevenly across that same photosphere, dark blemishes called sunspots appear and fade over days or weeks, patches noticeably cooler than the surrounding gas, because tightly bundled magnetic field lines there suppress the usual churning convection that carries heat up from below. Where that convection is throttled back, less fresh heat arrives at the surface, and the patch of photosphere sitting above the tangled field cools by a meaningful margin compared with its undisturbed neighbors nearby. A single sunspot typically shows a darker central region called the umbra, surrounded by a lighter, softer-edged ring called the penumbra, together forming a shape that has been sketched, catalogued, and counted by observers for centuries, using nothing more advanced than a telescope and a steady hand. Far from being a flaw or a failure in the sun's usual behavior, sunspots mark exactly where the star's magnetic field happens to be strongest and most concentrated at that particular moment, a visible signature of forces otherwise completely invisible from any distance. A dark patch on a bright star, and underneath it, nothing missing at all, only magnetism crowding out the usual flow of heat for a while. Despite looking almost black against the blinding photosphere surrounding them, sunspots are still, by any ordinary measure, extraordinarily hot, typically running a few thousand degrees cooler than their surroundings rather than cold in any absolute sense. Set beside the surrounding stretch of the sun's surface, that difference is enough to make a spot appear dark by comparison, the same way a lit candle looks almost invisible held directly against full daylight, despite still burning steadily on its own. Removed from the sun entirely and placed alone against a night sky, a single sunspot would still glow far brighter than anything produced on Earth, hot enough to outshine molten metal fresh from a furnace without any difficulty at all. This contrast explains why the dark patches were visible to careful early observers long before anyone had instruments capable of measuring their actual temperature directly, brightness alone being enough to mark them out clearly against their surroundings. Darkness here is entirely a matter of comparison, a shadow cast not by any absence of heat, but simply by everything nearby being hotter still. Some sunspots grow large enough to dwarf the planet these observations are being made from. Groups span tens of thousands of kilometers across, wide enough that several Earths could be set side by side within a single particularly large cluster. Early telescopic observers, including astronomers working within only a few decades of the telescope's invention, sketched and tracked these patches carefully enough to leave a record later observers could count against, though it took considerably longer to work out exactly what governed that pattern. Modern instruments have since measured individual spots and spot groups in precise detail, confirming that size varies enormously from one appearance to the next, some patches vanishing within a single day, while others persist, slowly changing shape for weeks at a stretch. A single cluster, large enough to be seen without any telescope at all, filtered safely, has occasionally appeared during Earth's own recorded history, drawing attention from observers who had no instrument beyond their own careful eyes. Scale on the Sun's surface is measured again and again against a planet that from up close looks anything but small. In 1843, a German astronomer named Samuel Heinrich Schwabe, after patiently recording sunspot numbers for well over a decade, announced a discovery nobody had confidently established before. The count of visible spots rises and falls in a roughly repeating pattern, lasting about 11 years from one quiet minimum to the next. What began as a personal, almost obsessive project, originally aimed at a different astronomical question entirely, turned into one of the most enduring patterns in solar science, confirmed and extended by generations of observers who followed his methods long after his own records ended. That 11-year rhythm is not perfectly regular, some cycles arriving a little early and others a little late, some producing far more spots at their peak than others manage. Yet the underlying pattern has held up across every cycle, reliably tracked since Schwabe's own patient counting began. Astronomers now number these cycles sequentially, each one identified by its position in an unbroken sequence stretching back to the earliest systematic records. A chain of counted patches connecting Schwabe's original notebooks directly to observations being logged today. One careful hobbyist's decade of counting quietly uncovered a rhythm hiding in plain sight. The Sun, as it happens, has been keeping that beat for as long as anyone has bothered to look closely enough to notice. Plot the latitude of sunspots against time across a full 11-year cycle. A distinctive shape emerges, one astronomers nicknamed the butterfly diagram for its resemblance to a pair of wings spreading outward from a central body. Early in each new cycle, spots tend to appear at higher latitudes, well away from the Sun's equator on both the northern and southern hemispheres, before gradually drifting closer to the equator as the cycle matures and eventually fades toward its next quiet minimum. This migration was first charted in detail by the astronomer Edward Walter Maunder and his collaborators in the early 20th century, working from decades of earlier sunspot observations gathered by other astronomers before them. Exactly why spots march toward the equator in this particular way remains tied to the same underlying magnetic dynamo responsible for generating the field in the first place. A connection researchers continue refining using increasingly detailed modern data, traced out patiently across more than a century of careful sunspot counting. That wing-shaped pattern still quietly hints at machinery working far below anything a telescope can see directly. Between roughly 1645 and 1715, a period now known as the Maunder minimum, sunspot counts recorded by observers of the time dropped dramatically below their usual level. Decades passing with only a small fraction of the spots that would normally be expected across a comparable stretch of cycles. That quiet stretch happened to overlap with a notably cold period across parts of Europe, sometimes referred to informally as the Little Ice Age, a coincidence that has drawn considerable scientific attention ever since it was first noticed by later researchers examining old astronomical records. Establishing a firm causal link between the two remains genuinely difficult, since Earth's climate responds to a great many influences at once, including volcanic activity and shifts in ocean circulation entirely unrelated to anything happening on the Sun. What researchers can say with more confidence is that the correlation is real and well documented in the historical record, even while the exact size of the Sun's own contribution to that particular cold stretch continues to be debated, not settled outright. A quiet Sun and a cold Europe once arrived together, and untangling exactly how much one caused the other remains an open thread in the story even now. Behind every sunspot, every 11-year rise and fall, and every migrating butterfly-shaped pattern lies a single underlying mechanism astronomers call the solar dynamo, a process by which motion inside an electrically conductive fluid generates and sustains a magnetic field. Inside the sun, that conductive fluid is the plasma itself, and the motion driving the dynamo comes from a combination of the star's own uneven rotation, spinning faster at the equator than near the poles, and the constant churning of the convective zone lying just beneath the visible surface. Together, these two motions stretch, twist, and fold the sun's magnetic field lines over and over, concentrating them in certain places, which is exactly where sunspots tend to appear on the surface above. Researchers building computer models of this process have managed to reproduce many of its broad features, including a roughly cyclical rise and fall in activity, though matching the precise timing and strength of any individual real cycle in advance remains considerably harder to achieve. Felt across the whole solar system, that magnetic rhythm ultimately comes down to little beyond hot, conductive gas, being stirred and twisted by the star's own uneven spin. That magnetic field does not simply hold steady once established. It flips its overall polarity, swapping magnetic north and south roughly once every 11 years, meaning a complete return to the field's original orientation actually takes about 22 years rather than 11. Researchers first confirmed this reversal by tracking the magnetic orientation of successive sunspot groups across multiple cycles, noticing that the pattern of polarity in one hemisphere consistently swaps sides from one 11-year cycle to the next before swapping back again during the cycle after that. Because of this longer underlying rhythm, some solar scientists prefer to describe the true magnetic cycle as spanning 22 years, with the more commonly cited 11-year figure describing only the rise and fall in sunspot numbers, rather than the full magnetic story sitting underneath it. Nothing about the sun's outward brightness changes dramatically during a reversal itself, the swap unfolding gradually and quietly across the peak of each cycle, never announcing itself with any obvious event visible from Earth. The sun's whole magnetic compass turns itself inside out roughly once a decade, and from any back garden, nothing about the swap can be seen happening. For all that researchers have learned about the broad mechanics of the solar dynamo, predicting the precise strength or exact timing of any future cycle in advance remains stubbornly difficult, an honest limitation acknowledged openly within the field rather than papered over. Several different research groups produce competing forecasts ahead of each new cycle, sometimes disagreeing by a wide margin on how active the coming years are likely to be, and the eventual outcome frequently falls somewhere outside the range any single model confidently predicted beforehand. Part of the difficulty comes from the sheer complexity of the underlying fluid motion. Small variations deep within the convective zone capable of growing over months and years into meaningfully different outcomes at the surface far above them. Long-term records stretching back through Schwaber's own original counts and beyond show enough irregularity, cycles of noticeably different strength and length scattered across the centuries, that no simple formula has yet managed to capture the pattern with real reliability. Documented this well for well over a century and a half, the rhythm still keeps its precise next beat a genuine secret from everybody currently trying to guess it. A thin, reddish layer rises just above the photosphere. Astronomers call it the chromosphere, ordinarily far too faint to see against the blinding disk beneath it, but briefly visible as a delicate pink or red rim during the fleeting minutes of a total eclipse, when the moon blocks the brighter light below it. That reddish color comes mainly from hydrogen gas glowing at a particular wavelength as it is energized by the layers beneath it. A signature so distinctive that spectroscopes can pick it out clearly even when the layer itself sits invisible in ordinary daylight. Early eclipse observers, centuries before spectroscopy existed as a formal science, described that same brief flash of color without fully understanding its cause, noting only that a strange rim of light appeared for a few seconds around the moon's dark silhouette. Compared with the photosphere below it, the chromosphere is considerably less dense, thin enough that its faint glow simply cannot compete with the far brighter light shining up from beneath it under normal daylight conditions. This whole layer of the sun's atmosphere hides in plain sight behind its own much brighter neighbor, and only steps forward for the handful of minutes when that neighbor happens to be covered. Threaded throughout the chromosphere, short-lived jets of plasma called spicules shoot upward from the surface like a field of narrow momentary flames, each one rising for several minutes before falling back or fading away, only to be replaced almost immediately by new ones nearby. At any given moment, an enormous number of these jets are active simultaneously across the sun's visible disk, giving the chromosphere, when observed in the right wavelength of light, a texture more like a restless field of grass, bending and swaying, than a smooth, calm layer. Exactly what triggers each individual spicule to rise remains an active area of study, with researchers generally connecting the process to the same tangled magnetic field lines responsible for so much else happening in this part of the sun's atmosphere. Material lifted by a spicule sometimes falls back down toward the surface, and sometimes escapes further outward instead, feeding into the layers above and contributing, in a small way, to the greater flow of material constantly leaving the sun altogether. Rising and falling every few minutes across the whole visible disk, this meadow of narrow, flame-like jets sits largely unnoticed just above the layer most people picture as the sun's true surface. Above the chromosphere, across a boundary only a few hundred kilometers thick, temperature does something that defies ordinary intuition entirely. Instead of continuing to cool with distance from the surface, as it does moving away from any ordinary heat source, it suddenly leaps upward by a factor of hundreds within an almost impossibly short span. Astronomers call this narrow, dramatic boundary the transition region, a thin shell separating the comparatively cool chromosphere below from the blisteringly hot corona waiting immediately above it. Nowhere else in the sun's structure does temperature change so abruptly across such a short physical distance, a jump far sharper than anything found deeper inside the star across layers many thousands of kilometers thick. And that single narrow boundary marks the true beginning of tonight's central puzzle, the exact place where the sun's atmosphere stops behaving the way common sense would predict. That boundary is barely a few hundred kilometers wide, and it separates a calm, familiar layer from one of the strangest puzzles left anywhere in modern astronomy. Beyond that narrow transition lies the corona, the sun's outermost atmosphere. And here, the numbers stop making the kind of sense a reasonable person might expect. While the visible photosphere below sits at roughly 5,500 degrees, the corona surrounding it runs to well over 1,000,000 degrees, and in places considerably higher still, by some measurements reaching several million. Ordinary experience teaches that heat fades the further one moves from its source, a fire feeling weaker several steps back, not stronger. Yet here the opposite happens. the sun's atmosphere growing dramatically hotter the further out from the visible surface it extends. This is not a small or easily dismissed discrepancy. It is a difference of hundreds of times the surface temperature, occurring across almost no distance at all. An enormous jump, packed into an almost negligible distance by astronomical standards. Physicists have spent the better part of the century trying to explain exactly how that reversal happens, testing idea after idea against measurements gathered from telescopes, eclipses, and more recently, spacecraft sent to sample the corona directly. Nothing quite like it exists anywhere else this channel has described so far. A star's outer edge running hotter than the bright surface it appears to be wrapped around. For most of history, the corona could only be seen at all during the brief minutes of a total solar eclipse, when the moon's disk blocked the far brighter light of the photosphere and allowed that faint, pale halo surrounding it to become visible against the darkened sky. Observers traveling to remote locations for these rare few minutes described a delicate, wispy crown of light stretching outward from the sun's edge, its shape shifting noticeably from one eclipse to the next, depending on how active the underlying magnetic field happened to be at the time. Because those precious minutes came so rarely and lasted so briefly, detailed study of the corona's physical properties advanced slowly for centuries, dependent entirely on whatever instruments a small team of astronomers could set up and operate correctly within the eclipse's narrow window. Only with the later invention of the coronagraph, an instrument that creates an artificial eclipse by blocking the photosphere's light with a solid disk inside the telescope itself, did continuous study of the corona become possible without waiting years between each real eclipse. A layer of the sun's own atmosphere spent most of recorded history glimpsed only in brief, precious minutes stolen from behind the moon's own shadow. 19th century observers studying the corona's faint light during eclipses noticed spectral lines that matched no known element on Earth, prompting some astronomers of the period to propose an entirely new element, tentatively named coronium, responsible for that mysterious glow. For decades, the puzzle went unresolved, coronium sitting alongside other once-proposed elements as a placeholder name for a signature nobody could otherwise explain, tested against every known substance without ever finding a convincing match in any laboratory. The eventual answer, arriving only in the 1940s through careful work by physicists including Bengt Edlin and Walter Grotrian, turned out to be both simpler and far stranger than a new element. Those unfamiliar lines belong to ordinary iron, but iron, stripped of far more of its electrons than any laboratory on Earth could easily reproduce at the time. Producing spectral lines of that particular kind required iron atoms to be sitting in an environment reaching well over 1 million degrees, since only that level of heat could strip away enough electrons to produce exactly the pattern of light being observed. A mystery element, imagined for decades, resolved in the end into something far more unsettling than a new substance. Solid proof that the corona really was, and still is, hotter than anyone had comfortably expected it to be. Once that identification was confirmed, astronomers were left holding a genuine paradox instead of a solved problem. Because everyday intuition about heat says warmth should fade with distance from its source, not intensify by a factor of hundreds across a boundary barely a few hundred kilometers wide. A fire burns hottest at its core and cools steadily further away. A stovetop element scorching close up, but merely warm from a short distance back. And almost every familiar heat source obeys that same basic pattern without exception. The corona breaks that pattern, sitting further from the sun's nuclear furnace than the visible surface does, and yet running measurably hotter than that surface by any instrument capable of measuring it accurately. Whatever mechanism is responsible has to be actively pumping additional energy into the corona from somewhere, since simple leftover heat radiating outward from the photosphere could never, on its own, explain a temperature climbing, not falling, with distance. That single stubborn contradiction, heat apparently flowing the wrong way across an ordinary-looking gap of empty space, has occupied solar physicists for the better part of a century, without one fully agreed answer yet in hand. One leading candidate for solving that puzzle goes by the name of nanoflares, a proposed swarm of extremely small, individually undetectable bursts of magnetic energy occurring constantly across the corona, each one far too brief and far too faint to register on its own, but adding up across billions of tiny events every second to a meaningful and continuous source of heating. The idea builds directly on the well-documented behavior of full-sized solar flares, much larger and more obvious releases of magnetic energy that will feature later tonight. Scaled down to a size so small that individual events simply blend together into what looks, from any distance, like a smooth and constant glow, instead of a series of distinct flashes. Supporting this idea directly has proven difficult, since instruments capable of detecting a burst that faint and that brief, scattered unpredictably across an area as vast as the corona, push right up against the limits of what current spacecraft can resolve clearly. Researchers analyzing subtle flickers in coronal brightness, gathered by spacecraft built specifically to hunt for exactly this kind of signature, have found evidence consistent with the idea, without yet delivering the kind of conclusive, direct detection that would settle the debate outright. A storm of tiny, invisible flashes, individually too small to matter, and collectively perhaps large enough to explain a whole mystery, remains one of the two strongest contenders on the table. A second, competing explanation looks not to small bursts of energy, but to waves, specifically a type called alphen waves, disturbances that ripple along magnetic field lines the way a plucked string vibrates along its own length, carrying energy up from the turbulent surface into the corona above it. Instead of releasing energy in sudden bursts, the way the nanoflare idea proposes, this mechanism suggests a steadier, more continuous transport. Magnetic energy generated by the constant churning of the convective zone traveling upward along field lines and gradually dissipating into heat once it reaches the corona's much thinner material. Spacecraft observations of the Sun's outer atmosphere have picked up wave-like motion, matching key predictions of this idea reasonably well, oscillations rippling through coronal structures at speeds and patterns broadly consistent with what the theory anticipates. Whether that wave energy, once detected, actually converts into heat efficiently enough to explain the full scale of the corona's extreme temperature remains the harder half of the argument to settle. A gap between observing the waves and proving they carry enough punch to do the whole job alone. Two very different pictures, one built from countless tiny explosions and the other from a steady hum of vibration, currently share the leading position in an argument neither has yet managed to win outright. Nanoflares and alphen waves need not be rival answers. A growing number of researchers now suspect that both mechanisms might be contributing simultaneously instead of competing for a single prize, each responsible for some share of the total heating, with neither one alone accounting for the whole effect. Untangling how much of the corona's extraordinary temperature comes from one process versus the other has proven genuinely difficult, since both mechanisms trace back to the same tangled, ever-shifting magnetic field, and both leave signatures that can, in certain observations, look frustratingly similar from a distance. Missions launched specifically to study this question in close detail, gathering measurements far closer to the Sun than any earlier spacecraft managed, were designed in large part to finally separate these overlapping signals from one another and settle which process dominates under which conditions. For now, solar physicists can describe the leading candidates in detail, rule out several older ideas that clearly fail to match the data, and still not offer a single, fully agreed final answer covering every part of the corona at once. Parker Solar Probe and Solar Orbiter now spend much of their working time gathering exactly the kind of joint measurement needed to weigh one mechanism against the other directly. Despite carrying a temperature that would vaporize almost anything instantly, the corona is, by ordinary standards, an almost unimaginably thin wisp of material. Its particles spread so far apart from one another that its actual density falls far below that of the best laboratory vacuum ever produced on Earth. Temperature and heat, in the everyday sense of something capable of burning skin on contact, are not quite the same thing physically. Temperature measures how fast individual particles are moving, while the sensation of burning heat depends heavily on how many of those fast particles are actually striking a surface within a given moment. With so few particles present in any given volume of the corona, even ones moving at extraordinary speed, the total energy delivered to anything passing through remains comparatively small, nothing like being plunged directly into the surface of the Sun itself, despite the eye-catching temperature figures involved. Spacecraft engineers designing missions to fly close to or even through parts of the corona rely heavily on this exact distinction, since surviving extreme temperature and surviving extreme heat transfer turn out to be two genuinely different engineering problems instead of one single obstacle. A region hot enough to sound like the most dangerous place in the entire solar system proves, once density enters the calculation, strangely gentle in the specific sense that actually matters for anything trying to pass through it. Built specifically to test these competing corona heating ideas up close, instead of from a comfortable distance, the Parker Solar Probe launched in 2018 on a mission unlike anything sent toward the Sun before it, aimed at flying repeatedly through the outer corona itself instead of merely observing it from afar. Named after Eugene Parker, the physicist whose theoretical work on the Sun's atmosphere will feature again shortly, the spacecraft carries a specially engineered heat shield, only about 11 centimeters thick, yet capable of holding everything behind it close to ordinary room temperature, while its own front face meets conditions that would destroy almost any other piece of engineered hardware within moments. Instead of orbiting the Sun at a single fixed distance, the probe follows a long, looping path that repeatedly swings close and then pulls back out again, gradually tightening that loop across dozens of passes to edge closer with each successive approach. Every close pass gathers fresh measurements of exactly the kind of magnetic and particle data needed to distinguish between nanoflares and Alf-Vane waves directly. Data that no earlier mission, observing only from much further out, had ever been positioned to collect with this level of detail. In December 2021, after several years of gradually tightening loops, the Parker Solar Probe achieved something no spacecraft had ever managed before. It flew directly through the corona itself, crossing what researchers identify as the boundary where the Sun's atmosphere effectively ends and the solar wind properly begins. Instruments on board recorded conditions consistent with the spacecraft passing briefly through structures tied to the Sun's own magnetic field. Evidence interpreted as confirmation that the probe had genuinely entered the corona instead of merely approaching it from just outside. Mission scientists announced the achievement carefully, comparing it to a spacecraft finally touching a star, a milestone reached only after decades of engineering work aimed at building a heat shield capable of surviving conditions that close. Each subsequent pass has continued gathering fresh data from progressively closer distances, adding directly to the pool of evidence researchers are using to weigh the nanoflare and alpha wave hypotheses against one another using new measurements, not models alone. Once observable only from tens of millions of kilometers away, the Sun has finally had a human-built instrument pass directly through its own outer atmosphere and report back what it found there. Making that close approach survivable required a heat shield built from carbon composite material only about 11 centimeters thick, engineered specifically to absorb and radiate away extraordinary heat, while the delicate instruments and electronics tucked directly behind it remain at close to room temperature throughout each pass. The shield's white-coated front face reflects a large share of incoming sunlight before it can even be absorbed, while the carbon material itself conducts remaining heat sideways and outward, not letting it build up and travel straight through toward the equipment sheltering behind it. Because the corona's actual density is so low, despite its blistering temperature, the total heat energy striking the shield during even the closest approaches, while still extreme, remains within a range engineers judged survivable, with the right combination of materials and careful orientation throughout each pass. Every instrument aboard depends on staying tucked precisely within that shield's narrow cone of protection, since drifting even briefly outside its shadow at closest approach would expose delicate hardware to conditions well beyond anything it was built to survive. Only that single hand's width of carefully engineered material stands between a working spacecraft and conditions able to strip electrons from atoms without any particular effort. A steady flow of charged particles streams continuously outward from the corona in every direction. Astronomers call it the solar wind, and it never stops blowing, carrying protons, electrons, and a small share of heavier ions away from the Sun and out across the entire solar system without pause, day or night, cycle after cycle. Unlike wind on Earth, driven by uneven heating of the atmosphere and shaped by weather systems that come and go, the solar wind flows continuously because the corona is simply too hot for the Sun's own gravity to hold every particle in place. A portion of that superheated material perpetually escaping outward, never settling back down. This constant outward flow fills the entire volume of the solar system with an extremely thin haze of particles, far too sparse to notice directly, yet dense enough, cumulatively, to shape comet tails, buffet planetary magnetic fields, and carry the Sun's own magnetic influence outward across enormous distances. Spacecraft instruments sample this flow constantly, tracking its density, speed, and composition as it drifts past on its way toward the outer edges of the solar system and beyond. Never once pausing for breath, that wind has been blowing steadily outward from this one star for as long as the corona itself has existed. That outward flow is not a single, uniform breeze, but splits broadly into two distinct types, commonly described as slow and fast solar wind, differing considerably in speed, depending largely on which particular region of the corona each stream happens to originate from. Slow solar wind typically travels at somewhere around 300 kilometers per second, tracing back to more complex, tangled regions of the corona, associated with denser, more active magnetic structures near the Sun's equator. Fast solar wind moves considerably quicker, reaching speeds closer to 700 or 800 kilometers per second, and tends to stream outward from regions called coronal holes, areas where the magnetic field opens directly outward into space instead of looping back down toward the surface. Both streams eventually blend together as they travel further from the Sun, colliding and interacting in complex ways that spacecraft instruments continue mapping in increasing detail. particularly around the boundaries where a fast stream catches up with a slower one released earlier. One star manages to produce not a single steady wind, but two distinct kinds at once, each tracing its own particular patch of corona back to its source. Long before any spacecraft directly measured a single particle of it, the physicist Eugene Parker predicted the existence of this continuous outward flow, purely from theory, publishing calculations in 1958 that showed the corona's extreme heat alone should be enough to overcome the sun's gravity, pushing material outward in a steady stream, never letting it simply drift as a static, unmoving atmosphere. At the time, the idea faced considerable skepticism from parts of the scientific community, since a continuously escaping stellar wind of this kind had never been observed anywhere, and ran against the prevailing assumption that a star's outer atmosphere should behave more like a calm, static envelope. Confirmation arrived only a few years later, when early spacecraft carrying particle detectors measured exactly the kind of steady outward flow Parker's calculations had described, vindicating a prediction built from equations instead of direct observation. In recognition of that original theoretical breakthrough, the very spacecraft built decades later to fly through the corona and study the wind's origin directly was named the Parker Solar Probe in his honor, a rare case of an instrument bearing the name of someone who correctly described what it would eventually go on to measure. As the solar wind streams outward, it drags a portion of the sun's own magnetic field along with it, stretching invisible field lines out across the entire solar system, not looped tightly close to the star, the way a bar magnet's field might behave in isolation. Combined with the sun's own rotation, this stretched field takes on a broad spiral shape as it extends outward, sometimes compared informally to the pattern traced by water leaving a rotating garden sprinkler, each fresh burst of field lines curving gradually away from a straight radial line the further it travels from its source. Spacecraft scattered at different distances throughout the solar system have mapped this spiral directly, confirming both its overall shape and the way it shifts subtly with each new stage of the 11-year solar cycle. This dragged-out field forms only the innermost portion of a far larger magnetic structure extending well beyond the planets, a subject already explored on an earlier visit to the outer solar system, not one tonight's journey needs to retrace in detail. This far from its own source, the sun's magnetic influence has still not finished shaping the materials streaming past it. Where solar wind particles eventually reach a planet carrying its own magnetic field, as Earth does, that field acts as a kind of shield, deflecting most of the incoming stream around the planet instead of allowing it to strike the atmosphere directly. Though near the poles, some of those particles still manage to funnel down along magnetic field lines that curve inward toward the surface, not around it, colliding with molecules high in the atmosphere and exciting them enough to release a soft, shifting glow of light, known on Earth as the aurora. Oxygen and nitrogen molecules struck this way release light of different colors, depending on both the type of molecule involved and the altitude at which the collision happens, producing the pale green, red, and occasionally violet curtains that have been described by observers living at high latitudes for as long as written record has existed. Stronger surges in the solar wind, tied to more active stretches of the sun's own cycle, tend to push these gentle curtains of light further from the poles than usual, occasionally letting them drift into view from latitudes that rarely see them under quieter conditions. A quiet, steady stream leaving one star, arriving as a slow curtain of color drifting across a night sky many millions of kilometers away. Despite all that heat and light pouring outward from the sun, the space it travels through carries almost none of it in any form that could be felt directly. Because temperature, in the ordinary sense the word is used every day, depends on particles bumping into one another closely and often enough to exchange energy through contact. Out in the near emptiness, stretching between the Sun and any planet orbiting it, particles are spread so thinly, drifting so far apart from one another, that meaningful contact of that kind almost never happens, leaving nothing there to register a temperature in the way a thermometer measures warmth in a room full of air. This is the real answer behind tonight's central puzzle. It is not that space is somehow cold in the way a winter night is cold, filled with chilled air pressing against exposed skin. It is that space, for the most part, has no substance present capable of carrying warmth from one place to another by touch at all. Energy still crosses that gap constantly, but it travels as light instead of as heat, a different kind of journey that depends on nothing standing in its way, only on eventually meeting something solid enough to absorb it. A star, blazing at millions of degrees, sits directly beside a gap that carries no warmth of its own, and neither detail contradicts the other, once the difference between light and heat is properly understood. Warmth only becomes something felt only once that traveling light finally strikes matter capable of absorbing it. Whether that matter is a planet's surface, a spacecraft's outer hull, or the skin on the back of a hand. Photons arriving from the Sun carry genuine energy the entire way across an empty gap. Energy that has nowhere useful to go and nothing to warm until it finally collides with atoms able to absorb it, at which point that energy converts into the jostling motion of particles that people actually experience as heat. Earth's atmosphere and surface intercept a tiny fraction of the Sun's total light output, absorbing it steadily enough to keep the whole planet within a range comfortable for the kind of chemistry that makes life possible. An outcome that depends on having something present to catch that light in the first place. Strip away the atmosphere and the ground both, and the same light arriving from the same star would continue on into the distance, carrying its energy onward indefinitely, delivering no warmth of its own, since nothing would be present to receive it. Heat has always needed somewhere to land, and empty space, almost by definition, offers it nowhere at all to do so. Astronauts, working outside a spacecraft in direct sunlight, experience this same principle in an especially direct and personal way, their suits recording a stark difference between whichever side happens to be facing the Sun and whichever side sits turned away into shadow at the very same moment. The sunlit side of a suit can climb to temperatures well above the boiling point of water, absorbing sunlight with nothing in between to soften or filter it the way Earth's own atmosphere does for anyone standing on the ground below. The shadowed side, meanwhile, can drop to temperatures far below anything typically experienced on Earth's coldest days, cut off from that same direct sunlight and surrounded instead by the same near-empty space that carries, on its own, effectively no warmth to offer. Engineers designing spacesuits and spacecraft hulls have to account for this extreme split constantly, building in materials and coatings specifically chosen to manage heat pouring in from one direction while very little arrives from any other. One human body, standing in direct sunlight with nothing but a suit and a visor for protection, can feel scorching heat and bitter cold simultaneously, separated only by which way it happens to be facing. Not every release of the sun's stored energy arrives as a steady, gentle stream. Among the more dramatic examples are solar flares, sudden, intense bursts of energy released when tangled magnetic field lines near an active sunspot region snap and reconnect into a simpler configuration, releasing stored magnetic energy across a period lasting anywhere from minutes to a few hours. That reconnection process accelerates charged particles to extraordinary speeds and heats the surrounding plasma dramatically, producing a burst of light across a wide range of wavelengths, from radio waves through visible light and on into X-rays, all released within a comparatively short and sudden event. Flares tend to occur far more frequently during the active peak of the 11-year sunspot cycle, when tangled magnetic regions are more common and more complex, and considerably less often during the quieter years surrounding each cycle's minimum. Because the light produced travels at the same speed regardless of wavelength, any effects a flare has on Earth's own upper atmosphere begin almost immediately after the event itself, arriving alongside sunlight, not trailing behind it by any noticeable delay. Somewhere on the visible disk, an invisible magnetic knot snaps quietly, and in minutes can release more energy than almost any comparable event recorded anywhere nearby. Astronomers classify solar flares by strength using a simple lettered scale. It runs from the weakest and most common class through progressively stronger categories, each successive letter representing roughly 10 times more energy released than the one before it. This system gives researchers a quick, standardized shorthand for comparing one flare against another, similar in spirit to scales used elsewhere in science for ranking events by size. And it allows records stretching back decades to be compared directly against far more recent observations gathered by modern spacecraft. Instruments dedicated to constantly monitoring the sun's output in X-rays track this classification automatically, cataloging every flare crossing the detection threshold as part of an ongoing, uninterrupted record extending back many solar cycles. Stronger flares occur considerably less often than weaker ones, following a pattern common to many kinds of natural events where small occurrences vastly outnumber large ones across any given stretch of time. Quietly logged by an automated instrument somewhere in orbit, a plain letter and number is usually all that marks the moment a tangled patch of the sun's magnetic field let go of its stored energy. Distinct from a flare, though frequently occurring alongside one, a coronal mass ejection involves an enormous bubble of plasma and magnetic field being hurled outward from the corona, carrying billions of tons of material away from the sun at speeds that can reach well over 1,000 kilometers per second in the most energetic cases. Where a flare releases its energy mainly as a burst of light, a coronal mass ejection instead throws actual material outward bodily, an expanding cloud of charged particles and tangled magnetic field traveling through space much like a slower, far more massive cousin of the ordinary solar wind streaming continuously in the background. Spacecraft positioned to watch the sun continuously have photographed these events directly, capturing the expanding bubble as it billows outward and gradually fades from view against the surrounding darkness of space. Not every coronal mass ejection happens to be aimed toward Earth, and the vast majority sail off harmlessly in some other direction, drifting outward through the solar system without ever passing anywhere near this particular planet. The sun occasionally exhales a whole cloud of its own material outward into space, most of it destined never to encounter anything on its way to the very edge of the solar system. In September 1859, astronomer Richard Carrington observed an unusually bright flash on the sun's surface, an event later understood to have been a powerful solar flare accompanied by a correspondingly large coronal mass ejection aimed almost directly at Earth. Within roughly a day, the resulting disturbance reached Earth's own magnetic field, producing auroras bright enough to be seen far closer to the equator than usual, and inducing enough stray electrical current in telegraph wires of the period to spark, and in some documented cases, keep operating briefly even after being disconnected from their normal power source. Telegraph operators at the time described the event with a mixture of confusion and fascination, a quiet historical curiosity now studied carefully by researchers interested in understanding just how large a solar storm can plausibly become. Modern infrastructure is considerably more extensive and more electrically sensitive than a 19th century telegraph network, which is part of why researchers continue studying the Carrington event closely, treating it as a useful benchmark for understanding the upper range of what the Sun has been shown capable of producing. Once, a flash of light on the Sun's surface reached all the way to a telegraph operator's desk on Earth, sparking quietly across a wire strung between two ordinary towns. Instead of treating events like flares and coronal mass ejections as unpredictable surprises, a network of spacecraft positioned specifically to watch the Sun now monitors it continuously, tracking its surface, its magnetic field, and its outward flow of particles around the clock without interruption. Missions dedicated to this task sit at carefully chosen vantage points, some directly between the Sun and Earth, and others watching from angles that provide advance notice of activity before it fully rotates into view from Earth's own perspective. Data gathered by these instruments feeds into forecasting centers that track solar activity the same steady, methodical way meteorologists track weather patterns on Earth, issuing routine updates on the Sun's current condition and flagging periods of heightened activity for anyone whose work depends on knowing about them in advance. This ongoing watch exists mainly as quiet, practical bookkeeping, a steady stream of routine measurements collected day after day, useful to satellite operators and power grid engineers going about their ordinary work. Not any cause for particular concern on an average night. The Sun shone largely unwatched for more than 4 billion years, and now has a small fleet of careful, patient instruments keeping a continuous, calm record of everything it does. Long before spacecraft, telescopes strong enough to resolve any surface detail or even a working theory of what stars actually were, a German optician named Joseph von Fraunhofer noticed something strange while testing a new instrument in 1814. Passing sunlight through a narrow slit and a prism produced not a smooth rainbow, but a rainbow interrupted by hundreds of thin, dark lines crossing it at specific, repeatable positions. Fraunhofer carefully catalogued nearly 600 of these lines, labeling the most prominent ones with letters that astronomers still reference today, without having any working explanation at the time for why they appeared or what they meant about the light's source. His careful, patient measurements, made using nothing more than glass, careful angles, and a steady hand, laid the entire technical groundwork for a field that would not fully mature until decades after his own death. What began as a curious pattern of interruptions in an otherwise smooth rainbow turned into the single most productive tool astronomers have ever had for learning what a distant, unreachable object is actually made from. Understanding why those dark lines appeared at all took several more decades of work by other scientists, who eventually connected each line to a specific chemical element, absorbing light at that particular wavelength as sunlight passed outward through the Sun's own cooler outer layers on its way to Earth. Every element, when heated, produces or absorbs light at a distinctive, repeatable set of wavelengths, a kind of fingerprint unique to that substance and reproducible reliably in any laboratory equipped to measure it carefully. And matching that pattern of dark lines in sunlight against fingerprints measured from known elements burned or heated in earthbound laboratories allowed scientists to identify, one by one, exactly which materials were present in the outer layers of the Sun, all without needing to travel anywhere near the star itself. This technique now called spectroscopy, quickly extended far beyond the Sun to distant stars and galaxies as well, becoming one of the foundational tools of modern astronomy, not a curiosity limited to a single nearby star. First noticed almost by accident, that pattern of missing colors eventually explained what a star, and later a whole universe, was actually built from. In 1868, astronomers studying the Sun's spectrum during a total eclipse noticed a bright yellow line that matched no known element previously catalogued on Earth, a signature strong and distinctive enough that the French astronomer Pierre Janssen and the English astronomer Norman Lockyer, working independently, both concluded it belonged to a new element. Lockyer proposed the name helium, drawn from Helios, the Greek personification of the sun, a fitting choice given that the element had been identified in sunlight itself long before anyone found a trace of it anywhere on the ground. It took a further 27 years before helium was finally isolated in a laboratory on Earth. Found in 1895, trapped within a mineral sample, confirming decisively that the element astronomers had already named after the Sun really did exist as ordinary, tangible matter after all. Helium remains, to this day, the only element in the periodic table first discovered somewhere other than Earth, an unusual footnote in the otherwise earthbound history of chemistry. The Sun, sitting 150 million kilometers away, managed to hand chemists a brand new element before anyone had ever held a sample of it in their own hands. None of this deep understanding of the Sun's composition, structure, or internal chemistry has ever required a single probe to reach anywhere close to its center, since every conclusion described so far comes from analyzing light collected patiently from a safe distance, instead of from any direct sample gathered inside the star itself. Spectroscopy tells researchers which elements are present and in roughly what proportion. Measurements of brightness and color reveal the temperature of whichever layer that particular light escaped from. And subtle shifts in the position of spectral lines, caused by motion toward or away from an observer, reveal how different regions of gas are moving. Combined with careful mathematical modeling built on well-established physics, these remote measurements allow astronomers to construct a detailed, testable picture of layers no instrument could ever physically survive visiting directly, from the boiling convective zone down toward the crushing pressure of the core itself. Every claim made so far tonight about temperatures, pressures, and internal structure ultimately traces back to this same basic method: careful, patient analysis of light that has already made its own long journey outward before ever reaching an instrument capable of reading it properly. Layer by layer, almost completely from the outside, a whole star has been mapped using little beyond very carefully measured light. One particular kind of particle, though, carries direct information from deep within the core itself. It is produced during fusion and slips outward almost instantly, not taking the tangled, drawn-out route light itself is forced to follow through the radiative zone. That alone turns an ordinary 2-second dash into the fastest message the Sun ever sends. A neutrino, born deep in the fusion-crushed core, reaches open space before the light produced in that same instant has even cleared the dense layers immediately surrounding it, let alone begun its own tens of thousand-year crawl toward the surface. That near-total lack of interaction is exactly what makes neutrinos so valuable scientifically, since a particle capable of passing through an entire star, essentially untouched, is also capable of carrying genuine, unfiltered information about conditions right at the source. Information light itself takes tens of thousands of years or more to deliver by comparison. Detecting something that interacts this weakly, however, poses an enormous practical challenge, since the very property that makes neutrinos useful also makes them extraordinarily difficult to catch using any ordinary instrument. That messenger, built to slip through almost anything without stopping, turned out to be exactly the kind of witness solar physicists most wanted to interview directly. Every single second, an almost incomprehensible number of solar neutrinos passes through the human body. Something like 100 trillion pass directly through it, without causing the faintest sensation or leaving behind any detectable trace. A constant, invisible flood that has been streaming through every living thing on Earth for as long as there has been anything alive to stream through. That number holds true day and night alike, since neutrinos pass through the entire bulk of the planet with almost the same ease they pass through open air. Meaning nighttime offers no meaningful shielding from a stream produced by a star currently sitting on the opposite side of the Earth. Detecting even a tiny fraction of that enormous flood requires enormous, carefully shielded instruments, often built deep underground, specifically to block out unrelated particles that would otherwise swamp the extremely rare, genuine interactions researchers are actually trying to measure. Despite the staggering number involved, actually catching a neutrino in the act of interacting with ordinary matter remains a rare enough event that entire specialized facilities exist purely to maximize the tiny odds of it happening at all. A flood of trillions passes through everyone listening tonight, every second, and almost none of it, across an entire lifetime, will ever once make genuine contact with anything solid. Starting in the late 1960s, physicist Raymond Davis Jr. built one of the earliest serious attempts to catch solar neutrinos directly. A large tank filled with hundreds of thousands of liters of cleaning fluid buried deep inside the Homestake gold mine in South Dakota, shielded by nearly a mile of solid rock from unrelated particles arriving from other directions. Occasionally, a passing neutrino would interact with a chlorine atom within that fluid, converting it into a detectable form of argon that Davis and his team could then carefully extract and count, providing a direct physical measurement of how many solar neutrinos were actually arriving at Earth. The result, once tallied carefully over years of patient counting, showed only about a third of the neutrinos that theoretical models of the Sun's core predicted should be arriving. A persistent shortfall that came to be known as the solar neutrino problem. For decades, that gap left scientists facing an uncomfortable choice between two possibilities. Either the models describing fusion inside the Sun's core contained some meaningful error, or something about the neutrinos themselves was not fully understood yet. Davis's careful, patient counting deep underground had uncovered a genuine puzzle instead of confirming what everyone already expected to find. The eventual resolution, arriving only around the turn of the millennium through further experiments, including one built inside a Canadian nickel mine, showed that the Sun's models had been correct all along, and the apparent shortfall came instead from a previously unknown property of neutrinos themselves. They can change from one of three known types into another as they travel, a process called neutrino oscillation, meaning Davis's original detector had only ever been sensitive to one of those three types, and was therefore always destined to miss a portion of the true total. This discovery carried an important consequence well beyond closing the solar neutrino problem, since a particle capable of switching between types during travel must, according to the physics involved, actually carry a small but non-zero mass, contradicting an earlier assumption that neutrinos were massless. Researchers involved in confirming this oscillation effect were awarded the Nobel Prize in Physics in 2015, recognition for resolving a puzzle that had quietly sat unanswered in solar physics for more than 3 decades. One underground tank and one stubborn mismatch with prediction ended up reshaping a small but fundamental piece of particle physics far beyond anything to do with the sun specifically. Sound waves, it turns out, ring continuously through the sun's entire interior, generated by the turbulent boil of gas rising and sinking just beneath the surface and reflected repeatedly between the surface and deeper layers below, setting up patterns researchers can detect and measure directly at the visible surface using extremely precise instruments. These are not sounds anyone could ever hear directly, since no air exists in the vacuum of space to carry them onward to an ear. But they are genuine pressure waves traveling through the sun's own material, the same basic way sound travels through air, water, or solid rock here on Earth. Millions of distinct vibration patterns overlap simultaneously across the sun's surface at any given moment, each one tracing a slightly different path through the interior, depending on its particular frequency, together forming a constantly shifting, extraordinarily complex hum locked within the star itself. Instruments dedicated to this kind of study measure tiny, repeating shifts in the surface's motion caused by these overlapping waves, translating what looks at first like meaningless surface flicker into a detailed picture of conditions far below anything a telescope could ever photograph directly. An entire star is quietly ringing like a vast, complicated bell. And for decades, almost nobody was listening carefully enough to notice. This technique, known as helioseismology, works on broadly the same principle geologists use to study Earth's own hidden interior, by measuring how earthquake waves travel through and reflect off different layers of rock far below the surface. Because sound waves travel at different speeds through material of different density, temperature, and composition, tracking exactly how each wave pattern bends, speeds up or slows down as it passes through the sun, reveals detailed information about conditions in regions no instrument could ever visit directly. Researchers using this method have confirmed and refined earlier estimates of the depth and structure of the radiative and convective zones, checking theoretical models built from other kinds of evidence against an independent physical measurement gathered a completely different way. And helioseismology has also proven capable of tracking activity happening on the far side of the sun, hidden from any direct view from Earth, by measuring subtle disturbances in the wave pattern caused by large sunspot groups rotating out of sight around the back. A method built originally to study earthquakes rippling through solid rock turned out to work just as well on a star built from boiling gas and plasma. Among the more striking results to come out of careful, sustained helioseismology, researchers have mapped detailed patterns of gas flow occurring beneath the visible surface, including large-scale currents of material circulating slowly between the equator and the poles at different depths within the convective zone. These deep flows, invisible to any ordinary telescope and detectable only through their subtle effect on the sun's ringing internal vibrations, are now understood to play an important role in shaping the overall solar dynamo, alongside the differential rotation and convection already described earlier tonight. Mapping how these flows change subtly across the 11-year cycle has become one useful tool researchers use when attempting, with only partial success so far, to forecast how active any upcoming cycle is likely to be. First noticed decades ago as a curious flicker in extremely precise surface measurements, that signal is now one of the most detailed windows solar physicists have into the machinery hidden directly beneath everything visible from Earth. Launched in December 1995 as a joint mission between the European Space Agency and NASA, the Solar and Heliospheric Observatory, generally known by its acronym SOHO, has kept a nearly unbroken watch over the Sun from a stable vantage point roughly 1.5 million kilometers from Earth, positioned specifically to maintain a constant, unobstructed view without the interruptions an ordinary orbit around Earth would introduce. Carrying a dozen separate instruments, the spacecraft has photographed the corona continuously using its own onboard coronagraph, tracked helioseismic vibrations across the surface, and monitored the composition and speed of the solar wind pouring outward, all from that same steady vantage point maintained for decades. Originally designed for a mission lasting only a few years, SOHO has instead operated for well over a quarter of a century, becoming one of the longest continuously running solar observation missions ever flown, and quietly outlasting nearly every spacecraft launched alongside it during the same period. Along the way, SOHO has also become, almost by accident, the single most prolific discoverer of comets in history, its wide-field images regularly catching small icy bodies passing close to the Sun that no ground-based telescope happened to be watching for at the same moment. The mission was built to study one star and turned into one of astronomy's most productive comet-hunting instruments, almost as a side effect of never looking away. NASA's Solar Dynamics Observatory, launched in 2010, continues that same tradition of constant watchfulness, with sharper eyes than SOHO's older instruments, capturing extremely high-resolution images of the Sun's surface and atmosphere across multiple wavelengths simultaneously, updated every few seconds, not every few minutes. That combination of speed and resolution allows researchers to watch individual flares, granulation patterns, and magnetic structures evolve almost in real time, not from a slower, coarser picture pieced together from images gathered further apart. Positioned in an orbit chosen specifically to keep it within continuous radio contact with a single ground station, the spacecraft downlinks an enormous volume of data daily, described at the time of launch as roughly equivalent to downloading a substantial music collection every single day of the mission without pause. Footage gathered by this single spacecraft has since become the visual backbone of countless documentaries, museum displays, and public presentations about the Sun, offering a level of moving, close-up detail that earlier missions could not capture. Already watched carefully for decades, the Sun gained in this one mission by far its sharpest and most continuously updated portrait yet. The Ulysses spacecraft broke from the usual pattern. Launched in 1990 through a joint effort between NASA and the European Space Agency, it did not orbit within the same flat plane as the planets, the way almost every other solar mission does, but instead used a close flyby of Jupiter's powerful gravity to bend its own path sharply out of that plane, settling into a long, looping orbit that carried it directly over the Sun's north and south poles in turn. No other mission before or since has managed quite the same trajectory, since reaching a polar solar orbit directly from Earth would require vastly more fuel than any practical spacecraft could realistically carry, making Jupiter's gravity assist the only workable route available. From that unusual vantage point, Ulysses measured solar wind properties, magnetic field structure, and particle behavior above regions never sampled directly by any earlier mission, confirming that conditions above the poles differ noticeably from conditions measured nearer the Sun's equator during the very same stretch of the solar cycle. The mission continued operating for close to 2 decades, completing multiple full passes over both poles across different phases of the solar cycle, before finally losing power in 2009. One carefully bent trajectory, gave researchers their only direct look so far at what the sun's own poles actually look like from directly overhead. More recently, the European Space Agency's solar orbiter, launched in 2020, has begun tightening its own path toward the sun's poles, using a series of gravity assists from Venus, gradually tilting its orbit further out of the planetary plane with each successive pass, in a plan reminiscent of Ulysses decades earlier, though carrying a far more capable set of modern instruments this time. Alongside close-range imaging of the sun's surface and atmosphere, Solar Orbiter carries instruments specifically designed to sample the solar wind directly as it streams past, combining, on a single spacecraft, both the remote imaging SOHO and the Solar Dynamics Observatory specialize in, and the close-up particle sampling the Parker Solar Probe was built to perform. Working in loose coordination with Parker Solar Probe, which approaches far closer to the sun but lacks a clear view of its own surface from directly behind that protective heat shield, Solar Orbiter provides simultaneous imagery that researchers can match directly against particle measurements gathered nearby at roughly the same moment. Together, this small, deliberately coordinated fleet of spacecraft now watches the sun from more angles and distances simultaneously than at any earlier point in the history of solar research. The sun was once studied only from a fixed vantage point on the ground. Now it has companies circling it from several very different directions all at once. Turn away from the sun itself for a moment and look instead at the ordinary blue sky stretching overhead. And the very same physics responsible for so much happening inside the star also shapes what that daylight looks like once it finally arrives. Sunlight reaching Earth's atmosphere contains every visible color mixed together. But as it passes through the surrounding air, shorter wavelengths of light, the blues and violets, scatter off tiny air molecules far more readily than longer wavelengths like red and orange. A phenomenon named Rayleigh scattering, after the physicist who first described it mathematically. Scattered in every direction across the entire sky, instead of traveling straight through in one line. That shorter blue light reaches an observer's eye from seemingly every point overhead at once, which is exactly why the whole sky glows a soft blue all over, instead of showing a single bright point where the sun itself sits. Violet light actually scatters even more strongly than blue, according to the pure physics involved. But the eye's own sensitivity to violet is weaker, and a portion of it gets absorbed higher in the atmosphere before reaching the ground, leaving blue as the color that dominates what people actually perceive when they look up. Scattered sideways by plain air alone, the sun's ordinary white light paints a whole sky a color the star itself never appears to be. That same scattering effect explains why sunsets and sunrises so often glow orange and red instead of staying white or blue the way the sky does at midday. A shift caused by how much atmosphere the light has to cross before finally reaching an observer's eye. Near midday, sunlight takes a comparatively short, direct path straight down through the atmosphere, losing only a modest share of its blue light to scattering along the way, and arriving largely intact. Near the horizon, at dawn or dusk, that same light instead travels a far longer path sideways through the atmosphere, giving far more opportunity for blue and green wavelengths to scatter away before the remaining light finally reaches the ground, leaving mainly the longer red and orange wavelengths behind to color the sky directly. Dust, smoke, and other fine particles suspended in the air can intensify this effect further, scattering additional wavelengths and sometimes producing especially vivid, deeply saturated sunsets following distant volcanic eruptions or large wildfires elsewhere on the planet. The same simple physics responsible for a plain blue midday sky rearranges itself twice a day into a different and far more colorful performance near the horizon. A further coincidence tied to the sun's appearance in Earth's sky involves the moon and not the atmosphere directly. The sun happens to be roughly 400 times wider across than the moon, while also sitting at the same time roughly 400 times farther away from Earth. A near-perfect cancellation that leaves both objects appearing almost exactly the same size when viewed from the ground. Because of that close match, the moon is occasionally able to pass directly in front of the sun and block its light almost completely. An alignment precise enough to produce the brief, striking spectacle known as a total solar eclipse, visible only from within a narrow strip of Earth's surface at any given time. During those few minutes of totality, with the blinding photosphere finally covered, the faint corona described earlier tonight becomes visible to the naked eye directly, offering one of the very few opportunities anyone on the ground has ever had to see that layer without specialized instruments. No law of physics requires this particular size and distance match to exist at all, and no other planet in the solar system is known to enjoy quite so precise a coincidence between any moon and its own star. Because that alignment depends on such an exact match between apparent size and precise geometry, total solar eclipses are rarer and briefer than many people assume. Visible from any single location on Earth only once every few centuries on average, and lasting, even at their longest, for a few brief minutes before the moon's shadow moves on and daylight returns in full. The narrow path along which totality can actually be observed, called the path of totality, is usually somewhere around 100 to 200 kilometers wide, occasionally more, spanning only a comparatively small strip of Earth's surface at any given moment, sweeping across the globe as the moon's shadow travels along its own orbital path. Outside that narrow strip, observers see only a partial eclipse, the moon covering some but not all of the sun's disk, a noticeably less dramatic event that never produces the same striking, sudden darkness or brief glimpse of the corona that totality delivers. Skilled eclipse chasers now travel considerable distances specifically to place themselves within that narrow path whenever a suitable alignment approaches, treating each brief appearance as a rare and carefully planned opportunity instead of something to be caught by accident. A shadow, only 100 kilometers wide or so, sometimes wider still, racing across the surface of a whole planet for only a few minutes at a time, is all that separates an ordinary afternoon from one of the more striking sights available anywhere in nature. This precise alignment is not a permanent one. The moon has been slowly drifting away from Earth for its entire history, moving outward by only a few centimeters each year, a rate first measured directly using reflectors left on the lunar surface by visiting astronauts decades ago. Slow as that drift is, measured across enough time, it steadily shrinks the moon's apparent size as seen from Earth, meaning it covers slightly less of the sun's disk with each passing million years than it did in earlier eras of the planet's history. Current calculations suggest that roughly 600 million years from now, by present-day models, the Moon will have drifted far enough away that it can no longer fully cover the Sun's disk from anywhere on Earth, bringing an end to true total solar eclipses altogether and leaving only annular eclipses, thin rings of light, in their place from that point onward. Long before that particular ending arrives, the Sun's own story will already be well underway toward changes larger and more dramatic than anything happening to the Moon's slow, steady drift. A coincidence precise enough to briefly reveal an entire hidden layer of a star is, on the scale of that star's own life, only ever going to be a temporary arrangement. Step back from all of this fine detail for a moment and consider where the Sun itself actually came from. A story that begins, by current models, roughly 4.5 billion years ago, inside a vast, cold cloud of gas and dust, drifting through this region of the galaxy long before anything resembling a star existed here at all. Somewhere within that cloud, a slightly denser clump began pulling inward under its own gravity, gathering more material as it went, and spinning faster the smaller and denser it became. The same basic principle that makes a spinning skater speed up by pulling their arms in close to their body. As that collapsing clump grew hotter and denser at its center, pressure and temperature eventually climbed high enough to ignite the very same fusion reactions still running inside the Sun's core today. Marking the moment, a mere clump of collapsing gas formally became a star in its own right. Everything else discussed tonight, every layer, every cycle, every stubborn open question about the corona, ultimately traces back to that single original collapse. One modest clump within one ordinary cloud, settling slowly into the star, currently keeping an entire solar system lit. Exactly what triggered that particular clump of gas to collapse remains an open question. Researchers continue investigating it, using indirect chemical evidence found in some of the oldest surviving material from the early solar system. One widely discussed hypothesis proposes that the shockwave from a nearby exploding star, a supernova, may have compressed part of that original cloud enough to tip it over the edge into collapse, seeding the resulting disk with certain short-lived radioactive elements whose fingerprints researchers have identified in ancient meteorites. Other researchers point out that clouds of this kind can also collapse without any such dramatic outside trigger, through their own slow, natural instability, given enough time and enough surrounding mass pressing inward. Because the direct evidence is limited to what survives, billions of years later, inside a small number of ancient rocks, no single explanation has been confirmed decisively over the others just yet. A story that ends with an entire solar system still carries, right at its very beginning, a genuine and only partly answered mystery of its own. In its earliest years as a star, the young Sun almost certainly passed through a turbulent phase. Astronomers call it the T-Tauri phase, named after a similar young star observed elsewhere, a stretch marked by irregular brightness, occasional dramatic outbursts, and a stellar wind stronger and more forceful than the comparatively gentle, steady flow streaming outward from the Sun today. That early, forceful wind is thought to have helped clear away much of the remaining gas and dust still surrounding the young star, sweeping loose material outward and shaping the disk left behind into the more organized structure that would eventually give rise to planets. Researchers studying other young, sun-like stars, still passing through this same turbulent phase elsewhere in the galaxy, have been able to observe directly many of the same processes the young Sun itself is presumed to have experienced billions of years ago, offering a kind of living comparison impossible to obtain from studying an aging star firsthand. By the time that turbulent early phase settled down, the Sun had already largely become the far steadier, more predictable star described throughout most of tonight's journey. A star's calmest, most reliable stretch of life was preceded by a rowdier beginning than anything visible from Earth's own sky today. Everything else orbiting the Sun today, from the rocky planets closest to it, out to the icy, distant bodies scattered far beyond Neptune, formed from the same swirling disk of leftover gas and dust that surrounded the young star in the aftermath of its own formation. Material that never quite made it into the Sun itself. Closer to the young star, where temperatures ran too high for ice to survive, smaller grains of rock and metal gradually collided and stuck together, building up over time into the rocky planets found in the inner solar system today. Farther out, where the disk stayed colder, ice could persist alongside rock and gas, allowing larger bodies to accumulate, eventually growing into the gas and ice giants this channel has already described on earlier visits to the outer solar system. Nearly every object orbiting the Sun today, in other words, is built from the very same original supply of raw material, sorted by little more than distance from the newborn star and the temperature that distance happened to allow. One star's early, messy leftovers became an entire system of planets, moons, and everything currently orbiting alongside them. Determining the Sun's precise age has depended less on studying the Sun itself directly, and more on studying some of the oldest surviving material left over from its own formation, specifically ancient meteorites that have drifted largely unchanged since the earliest days of the solar system. Using radiometric dating, a technique that measures the steady, predictable decay of certain radioactive elements trapped within these rocks since they first solidified, researchers have consistently arrived at an age for the solar system, and therefore for the Sun itself, of roughly 4.5 billion years. A figure refined repeatedly as measurement techniques have improved over decades. Because the Sun and its surrounding planets formed together from the very same collapsing cloud within a comparatively short span of time, astronomically speaking, dating the oldest meteorites effectively dates the Sun as well, even though no instrument has ever measured the star's own material directly for this purpose. This approach illustrates something already touched on earlier tonight, that much of what is confidently known about the Sun comes not from sampling the star itself, but from careful, patient study of everything scattered around it instead. A star's own birthday, in the end, was read not from the star, but from the oldest scraps of debris still drifting nearby. By current models, the Sun sits roughly midway through the longest and most stable stretch of its entire life. A phase astronomers call the main sequence, during which a star steadily fuses hydrogen into helium at its core, while maintaining a broadly consistent size, brightness, and temperature across an enormous span of time. Stars remain on the main sequence for as long as their core retains enough hydrogen fuel to sustain the fusion reactions, holding the delicate balance between gravity and pressure steady. A stretch that, for a star of the Sun's particular mass, is expected to last roughly 10 billion years from beginning to end. Having already spent somewhere close to 4.5 billion of those years fusing steadily away, the Sun has, by these same estimates, a comparable stretch still ahead of it before conditions in the core begin to shift in any dramatic way. Throughout this entire stable stretch, the Sun has been gradually brightening by a small but measurable amount. A slow trend that current models expect to continue steadily onward for the remainder of its time on the main sequence. Roughly halfway through its own long, stable career, the Sun continues, largely unbothered, doing precisely what it has been doing for over 4 billion years already. Eventually, according to the same models used to trace the Sun's history so far, the hydrogen fuel available within the core will grow scarce enough that fusion there can no longer proceed at its current steady rate. An event expected, by current calculations, somewhere in the neighborhood of 5 billion years from now. As core fusion slows, the delicate balance between gravity and outward pressure that has kept the Sun steady throughout its main sequence life begins to shift, with fusion instead migrating outward into a shell surrounding a core that is itself gradually contracting and heating further under its own weight. That renewed contraction paradoxically drives the star's outer layers to expand dramatically, not shrink, since the increased energy pouring out from the intensifying shell of fusion pushes those outer layers outward, even as the core itself continues collapsing inward. This marks the beginning of the red giant phase, a dramatic and well-documented stage in the life of stars of the Sun's particular mass. One astronomers have modeled in detail using exactly this kind of gradual core collapse and outward swelling envelope. Billions of years of remarkable steadiness end here. Once the core fuel finally runs thin, the shape of a star changes more dramatically than at any other point across its whole life. During that red giant phase, current models suggest the Sun will expand enormously, its outer layers swelling outward to a size large enough to swallow Mercury and Venus, the two innermost planets currently orbiting comfortably within its warmth today. As the outer layers expand this dramatically, they also cool compared with the Sun's current, much more compact form, shifting the star's overall color from its familiar white toward a deep orange or red, giving this entire phase of stellar life its descriptive name. Despite that enormous increase in physical size, the expanding star's overall luminosity climbs substantially as well, meaning any remaining planets further out would actually receive more total energy during this phase than they do from the Sun's current, far more compact and comparatively modest output. Astronomers studying other stars elsewhere in the galaxy, currently passing through their own red giant phase, have observed this same general pattern repeatedly, providing considerable confidence in the broad outline of what current models predict lies ahead for the Sun specifically. Two planets currently sitting comfortably close to a modest, well-behaved star will one day find themselves swallowed by the very same star, grown dramatically larger around them. What actually happens to Earth during this dramatic expansion remains an unsettled question among researchers, instead of a confidently agreed conclusion, since the outcome depends on several competing factors that current models have not yet fully resolved against one another. On one hand, the expanding outer layers might grow physically large enough to engulf Earth's current orbit directly, swallowing the planet outright, the same way Mercury and Venus are expected to be consumed. While, on the other hand, the Sun is also expected to lose a meaningful fraction of its own total mass during this phase, weakening its gravitational pull and allowing Earth's orbit to drift gradually further outward over the same stretch of time, potentially carrying the planet just barely beyond the reach of the swelling star, even as it grows dramatically larger. Different research teams running slightly different versions of these models have reached different conclusions on which of these two competing effects ultimately wins out, making Earth's precise fate during this era one of the more open questions in current solar and planetary science. Built from little beyond gravity, expanding size and gradually shifting orbits, the calculation has, so far, refused to settle cleanly into one confident answer either way. Deeper inside that same expanding red giant, once conditions in the core grow hot and dense enough, a new fusion process ignites, involving helium, not hydrogen, a reaction physicists call the triple alpha process, in which 3 helium nuclei combine to form a single nucleus of carbon, releasing a fresh burst of energy from a different nuclear reaction than the one that powered the Sun throughout its earlier, longer main sequence life. This transition marks the beginning of what astronomers call the horizontal branch phase of a star's evolution, during which the star settles into a somewhat more compact and stable configuration than the earlier red giant stretch, now burning helium steadily at its core, while a thinner shell of hydrogen continues fusing in a layer surrounding it. Stars of the Sun's particular mass are expected to remain in this helium-burning stage for a shorter stretch of time than they spent on the main sequence earlier, since helium fusion, while still substantial, proceeds through a shorter and less efficient chain of reactions overall. Telescope surveys have catalogued large numbers of stars caught in exactly this helium-burning state. Direct observational support for a phase the Sun itself has not yet reached, but is expected, by current models, to enter in its own turn. Billions of years spent fusing hydrogen give way here to a different fuel, taking over once the first one finally runs out. Once even that supply of helium at the core begins running low in turn, the outer layers of the aging star grow increasingly unstable, eventually drifting away into space as a slowly expanding shell of gas, illuminated from within by the hot, exposed core left behind. An object astronomers call a planetary nebula, despite having, somewhat confusingly, nothing directly to do with planets in the ordinary sense of the word. Countless examples of these glowing shells have been photographed in exquisite detail throughout the galaxy, each one marking the final, outward breath of a star broadly similar in mass to the Sun, its outer material drifting outward over thousands of years, while gradually fading and dispersing into the surrounding interstellar medium. The particular shape and structure of any given planetary nebula depends heavily on the exact details of how that star's outer layers were shed, producing an enormous variety of forms, some resembling rings, others hourglasses, or more irregular, wispy shapes scattered unevenly across the sky. Current models predict the Sun will eventually produce a planetary nebula of its own in this same general way, a brief, beautiful final display, astronomically speaking, before that particular chapter of its story closes for good. Not every stellar ending is a quiet fade. Sometimes it is a slow, glowing exhale, visible across enormous distances for a comparatively short stretch of cosmic time. What remains after that outer shell has drifted away is a small, extraordinarily dense object called a white dwarf, essentially the Sun's own exposed core, left behind once every outer layer capable of further fusion has already been shed into space around it. Current models suggest this remnant will pack roughly half the Sun's original mass into a sphere only about the size of Earth, an object so dense that a single teaspoon of its material would weigh, by comparison with anything found on Earth's surface today, an amount measured in tons instead of grams. No further fusion occurs inside a white dwarf of this kind, since it lacks sufficient mass to reignite any further nuclear reactions, leaving it instead to radiate away its remaining store of heat slowly into space across an extraordinarily long stretch of time, cooling gradually, never continuing to shine through any active internal process. Current calculations suggest that a white dwarf of this size takes far longer to cool completely than the current age of the entire universe, meaning not a single one has yet had time to fully cool down anywhere, regardless of when it originally formed. What began as an entire star, blazing brightly enough to warm a whole system of planets, ends, by current models, as a small, dim ember still cooling patiently, long after everything else about it has already changed beyond recognition. Formally, astronomers classify the Sun as a G-type main sequence star, a designation built from a standardized system that sorts stars primarily by temperature and color, instead of by size or brightness alone, placing the Sun comfortably in the middle of that particular scale, not at either extreme. The informal nickname yellow dwarf is often attached to stars of this exact class, a label that, as already described earlier tonight regarding the Sun's true color, is somewhat misleading in the strictest sense, since the Sun itself actually shines closer to white than to true yellow once atmospheric scattering is properly accounted for. Despite that slightly inaccurate nickname, the formal classification itself remains scientifically precise and useful, allowing astronomers to compare the Sun directly and consistently against millions of other stars, catalogued using exactly the same standardized temperature-based system. This same classification framework groups stars into a small handful of major categories, running from extremely hot, blue-white giants down through progressively cooler and redder types, with the Sun's own G classification sitting solidly in the middle, not toward either extreme of that full range. A star nicknamed for a color it does not quite have still earns its formal letter grade honestly, based on temperature measured carefully, not guessed from any casual first impression. Set against the full range of stars catalogued throughout the galaxy, the Sun turns out to be a fairly ordinary, unremarkable example in terms of raw size and mass, neither among the largest nor among the smallest stars known to exist by any meaningful margin. Some stars dwarf the Sun so completely that, placed at its center, their outer layers would extend well past the orbit of Jupiter, swallowing several planets in the process, while other stars run so small and dim that a dozen or more of them could be packed comfortably within a volume the size of the Sun alone. Statistically speaking, stars smaller and cooler than the Sun outnumber stars larger and hotter than it across the galaxy as a whole, meaning the Sun sits, in terms of raw population, closer to the larger and brighter end of stars generally, not sitting at any true midpoint by sheer numbers. Yet none of this ordinary standing diminishes anything already described tonight about the Sun's own particular behavior, its magnetic cycles, its unresolved corona, and its slow, steady fusion, all of which remain its own, regardless of how it compares statistically against its neighbors. A thoroughly ordinary star, by the numbers, still turns out to be the most consequential object in the sky for every living thing currently depending on it. Interested in finding stars similar to the Sun, not merely comparable in broad category, astronomers have spent decades searching for what they call solar twins, stars matching the Sun's temperature, mass, composition, and age closely enough to serve as a natural comparison point. A way of checking whether the Sun's own particular behavior is typical for a star of its exact type, or unusual in ways not yet fully appreciated. Genuine solar twins have proven rarer than early searches expected, since matching every relevant property simultaneously, not just temperature or size individually, but the full combined profile, turns out to be a demanding standard very few stars actually satisfy closely. A small number of strong candidates have been identified over the years regardless, studied in detail specifically to see whether they share the Sun's own magnetic cycles, sunspot patterns, and general behavior, or whether the Sun's own particular rhythm is, on closer comparison, somewhat unusual, even among stars closely matching it on paper. Comparing the Sun against its closest known analogues elsewhere in the galaxy offers researchers one of the few practical ways to judge whether anything described tonight about this particular star is representative of stars generally, or, in certain specific respects, something closer to a genuine outlier. measured continuously by a succession of dedicated spacecraft positioned specifically for the task. The total amount of solar energy reaching a given area of space at Earth's own distance from the Sun, a figure researchers call the solar constant, or total solar irradiance, comes out to roughly 1,360 watts per square meter when measured just outside Earth's own atmosphere. Despite its name, that figure is not perfectly fixed, drifting by a small but measurable amount across the 11-year solar cycle, rising slightly during periods of peak sunspot activity and easing back down again during quieter years, a subtle rhythm only detectable using instruments precise enough to catch a change amounting to a small fraction of 1%. Tracking this figure continuously across multiple overlapping spacecraft missions, carefully calibrated against one another to maintain a single unbroken record, has allowed researchers to build a long, consistent history of exactly how much energy the Sun has actually delivered to this part of the solar system decade after decade. That same steady figure, once it reaches Earth's own atmosphere and surface, becomes the entire foundation for the planet's climate, its weather, and ultimately, every living thing depending on that energy to survive at all. Measured patiently and continuously from orbit, that one number underwrites everything warm happening anywhere on the surface of this planet. Carried outward first by the solar wind, and then stretched into its broad spiral shape by the Sun's own rotation. The star's magnetic influence extends its reach across the entire solar system, shaping an enormous, invisible structure that dwarfs the orbit of every planet combined, an environment researchers refer to collectively as the heliosphere, already touched on briefly during an earlier visit to the outer solar system. Every planet, comet, and stray fragment of debris currently orbiting the Sun sits somewhere within that same invisible bubble. Its trajectory, and in some cases, its very atmosphere, shaped continuously by a magnetic influence originating from a star sitting, by comparison, an extraordinarily short distance away at the very center of it all. Spacecraft launched decades ago and still traveling steadily outward have measured this influence firsthand as they pass through it, tracking exactly how the Sun's magnetic reach and the density of its particle wind change gradually the further any given instrument travels from its original source. Everything described across tonight's entire journey, every layer inside the star, and every particle streaming away from it ultimately contributes to shaping this one enormous invisible structure wrapped loosely around an entire system of worlds. The Sun sits at the very center of it all, and still manages to leave its own particular signature stamped across every corner of the space surrounding it. Return finally to the corona itself. One detail becomes clear only once every other layer described tonight has already been laid out in order. That scorching outer atmosphere has no sharp outer boundary at all. No clean edge where it stops and interplanetary space properly begins in any strict sense. Instead, the corona thins gradually with distance. Its extraordinary heat and its outward streaming material blending seamlessly into the solar wind already described earlier. The two effectively becoming the same continuous flow the further out any given measurement is taken. Researchers studying this gradual transition have found no single universally agreed distance at which the corona formally ends and the solar wind formally begins, treating the boundary instead as a matter of definition and convenience, not as any hard physical line
a spacecraft might cross and register directly.
Then, in effect, the same overheated atmosphere responsible for tonight's central puzzle never truly stops. Its influence thinned and cooled by distance, but never fully switched off, reaching past every planet in the system regardless. Already strange enough for running hotter than the surface beneath it, that layer has, on closer inspection, no proper edge marking where it ends either. After everything gathered across decades of careful observation, from Fraunhofer's first puzzling dark lines, through helioseismology's ringing interior vibrations, and the Parker solar probe's direct pass through the corona itself, the precise mechanism responsible for heating that outer atmosphere to hundreds of times the temperature of the surface below it is still an open question. And everyone working on it says so plainly. Solar Orbiter and Parker Solar Probe now fly in loose coordination, specifically to close that gap. One spacecraft images the magnetic structures visible from a distance, while the other samples particles and fields from deep inside the corona itself, matching each picture against measurements gathered only minutes apart. That combination lets researchers weigh the nanoflare and Alf-Vane wave signatures against real conditions, not only against models, something no earlier mission flying further out was ever positioned to do. Few questions this thoroughly instrumented and this directly measured at close range anywhere else in modern astronomy remain quite so openly unresolved as this particular one. Even the star sitting nearest to Earth, watched this closely for this long, still keeps one unanswered question tucked inside its own outer atmosphere. Weighed against everything described tonight, from the crushing 15 million degrees buried at the very center, out to the strange, unexplained heat of the corona wrapped loosely around the outside, one plain detail remains steadier than any of the individual mysteries along the way. The same basic process, hydrogen nuclei fusing into helium deep within that core, has been running continuously without any meaningful interruption for something close to 4.5 billion years already. No engineer designed that process. No external control keeps it running smoothly, and nothing about it has changed in any way large enough to notice across the entire span of human history, or indeed across the entire span of life on Earth, stretching back long before any human existed to notice anything at all. Every sunrise, every shifting season, every quiet afternoon warm enough to feel directly on your skin, traces back to that same unbroken, self-sustaining reaction, running steadily inside a star currently sitting roughly midway through its own extraordinarily long life. Lit roughly 1 billion years before the earliest life on Earth existed to benefit from it, that furnace has kept burning steadily and reliably, day after day since, unnoticed by nearly everyone it has ever kept warm. Photograph the sun's disk carefully, and one more subtle detail becomes visible. The very edge, or limb, of that disk appears noticeably dimmer than the center, a pattern astronomers call limb darkening, instead of any genuine unevenness in the star's own output. Looking straight at the center of the disk, an observer's line of sight plunges more or less directly down into the photosphere, reaching slightly deeper, hotter layers before the light finally escapes toward Earth. Looking instead toward the edge, that same line of sight cuts through the photosphere at a shallow, glancing angle,
gathering light from higher, noticeably cooler layers that never quite reach the same brightness as the material glimpsed directly underneath the center. Because temperature and brightness are so closely linked in a layer this thin, that shift in viewing angle alone is enough to make the rim of the disk look consistently softer and dimmer than the middle, without any change whatsoever in what is actually happening inside the star. One trick of geometry shapes the shading of a whole stellar disk. The same principle, at a vastly different scale, behind why a sphere lit from one side always looks brighter at its center than along its curving edge.
Magnetic field strength across different regions of the Sun can be measured directly, without ever sending an instrument anywhere near the surface, using a phenomenon called the Zeeman effect, in which a strong magnetic field splits a single spectral line into two or more closely spaced lines whenever light passes through it. The stronger the surrounding magnetic field, the further apart those split lines drift from one another, giving researchers a precise, physically grounded way to measure field strength directly from the pattern captured in an ordinary spectrum gathered from Earth or from orbit. Applied to sunspots specifically, this technique confirmed that the darker regions described earlier really do correspond to unusually concentrated bundles of magnetic field, with splitting strong enough in the larger spots to be measured clearly even using instruments built decades ago. Modern solar telescopes now map this splitting continuously across the entire visible disk, producing detailed charts of magnetic strength and direction that update constantly as sunspots form, grow, and eventually fade away again. First noticed and explained in a laboratory on Earth, one split line in an otherwise ordinary spectrum became one of the most reliable tools available for reading a star's own invisible magnetism from a comfortable distance. Current models of stellar evolution predict that the young Sun, several billion years ago, shone with somewhere between 20 and 30% less total output than it does today, a gradual brightening tied directly to the slow buildup of helium at the core, already described earlier tonight. That prediction creates a genuine and long-debated puzzle once compared against geological evidence gathered from early Earth, since rocks and mineral deposits from that same ancient period consistently point toward a planet warm enough to host liquid water, not one frozen solid under a noticeably dimmer star. Researchers call this mismatch the faint young sun paradox, and proposed solutions have ranged from a much thicker blanket of greenhouse gases surrounding early Earth to subtle differences in the young planet's reflectivity, with no single explanation yet accepted as fully settled across the field. Evidence bearing on the problem continues arriving from multiple directions at once, including detailed studies of ancient rock formations on Earth and comparisons against other young sun-like stars observed elsewhere, still going through the same early, dimmer stage of their own lives. The Sun is confidently expected to have been fainter in its youth, and it still leaves researchers working out exactly how a young Earth, warmed by that fainter light, ever managed to keep liquid water flowing across its surface. Spacecraft like SOHO and the Solar Dynamics Observatory gather visible and ultraviolet light. Radio telescopes positioned across Earth's surface listen for something different, a completely different signature of activity in the corona, picking up bursts of radio emission produced when fast-moving particles, accelerated during flares and coronal mass ejections, interact with the magnetic field and thin plasma surrounding them. Certain categories of these radio bursts, catalogued by researchers using a simple numbered system, correspond closely to specific kinds of eruptive events, allowing ground-based observatories to detect and characterize activity happening in the corona using instruments cheaper and easier to maintain than any spacecraft. Because radio waves of different frequencies originate from different heights within the corona, tracking how a burst shifts frequency over the course of a few minutes lets researchers estimate how quickly a burst of particles is moving outward through the corona and into the solar wind beyond it. This radio-based method has been running in some form since shortly after the technology itself matured in the middle of the 20th century, providing an unbroken, independent record of coronal activity stretching back decades before spacecraft-based monitoring existed at all. Information about the sun's most violent moments does not always arrive as light visible to any eye. Sometimes it arrives instead as a faint crackle of radio noise picked up by antennas scattered patiently across the ground. We began this journey with the plainest possible view. A small, bright disk overhead that outshines every other star in the sky, and traced a path down through crushing fusion at the core, out through a slow, wandering crawl of light, taking tens of thousands of years to reach the boiling surface. And further still, into an atmosphere that runs against every ordinary expectation, far hotter the farther out it extends. We followed a wind that never once stops blowing, traced a magnetic field that flips its own polarity every 11 years, and stood alongside a spacecraft that finally, after decades of careful engineering, flew directly through that impossibly hot, remarkably thin outer atmosphere and reported back what it found there. We answered, as honestly as the physics currently allows, the very question this evening opened with: why a star felt so plainly on your skin from 150 million kilometers away still leaves the space in between with no warmth of its own. Because warmth needs matter to land on, and empty space offers it almost none. And we looked forward too, past red and swollen expansion, past a final glowing shell drifting slowly outward, toward a small, dense ember that will still be quietly cooling long after everything described tonight has finished happening. If tonight's kind of unhurried company is something you would enjoy more of, the subscribe button will be sitting there whenever you decide to use it. For 4.5 billion years, that star has burned without once stopping, and it will still be burning while you sleep. Rest well and sleep gently.